we thought we were looking for another Earth. Instead, we found nightmares. Planets where it rains molten glass, worlds so hot their atmospheres glow in the dark. Places where the wind moves faster than sound and nothing like life could survive. And these aren't rare exceptions, they're everywhere. For decades, scientists have been searching the galaxy for a second home, a place with oceans, air, and the right conditions for life. And eventually we found planets, thousands of them. But the closer we looked, the stranger they became. Tonight, we're going to explore some of the most extreme and unsettling worlds we've discovered in our search for Earth 2.0. Let's begin. To understand why the search for another Earth matters so deeply, you have to go back to a very simple and very human feeling. The feeling that this cannot be it. That the universe, 400 billion stars in this galaxy alone, and somewhere between 2 trillion and perhaps infinitely more galaxies beyond, cannot have produced only one small, wet, living world. Statistically, emotionally, philosophically, it just does not make sense. So scientists got to work, and the early days of that work were humbling in the best possible way. For most of human history, we could not even confirm that other stars had planets. We suspected it. Philosophers argued about it. But proof was another matter entirely. The stars are so impossibly far away that even our best telescopes for most of the 20th century could not resolve a planet orbiting one of them. A planet next to a star is like a firefly sitting next to a lighthouse, and you're watching from 3,000 miles away. The firefly is not going to be easy to spot. So scientists got clever. Instead of trying to see the planets directly, they started looking for what the planets do to their stars. 2 methods became the workhorses of the whole field. The first is called the transit method, and it is beautifully simple in concept. If a planet passes between its star and us, it blocks a tiny fraction of the star's light, an almost imperceptibly small dip in brightness, like a moth flying briefly in front of a lamp. If you see that dip repeat consistently at regular intervals, you know something is orbiting that star. You can figure out the planet's size from how much light it blocks. You can figure out its orbit from how often it crosses. It is elegant and it works, and it is how the majority of confirmed exoplanets have been found. The second method is the radial velocity technique, sometimes called the Doppler wobble method, and it is even more indirect. When a planet orbits a star, both objects are actually orbiting their shared centre of gravity. The star wobbles, almost imperceptibly but measurably, as the planet pulls on it. This wobble shifts the star's light slightly toward the red end of the spectrum when it moves away, and toward the blue end when it moves toward us. By measuring those shifts with extraordinary precision, astronomers can detect the presence of a planet they cannot see, and work out something about its mass. These 2 techniques together have given us a catalogue that, as of right now, contains more than 5,800 confirmed exoplanets, and the count is rising every year. NASA's Kepler Space Telescope alone, which stared at a single patch of sky for 9 years before its fuel ran out in 2018, added thousands of candidates to the list. Its successor, the TESS telescope, has been continuing the search since 2018, and above all of them now sits the James Webb Space Telescope, the most powerful observatory ever placed in space, peering into the atmospheres of distant worlds with a sensitivity that was considered science fiction just 20 years ago. So the search for Earth 2.0 is not just a dream anymore. It is a structured, funded, internationally coordinated scientific campaign, and it has been producing results. The only problem is that most of those results have been deeply, magnificently, sometimes almost comically terrible. Because what scientists discovered world after world is that the universe is extraordinarily good at making planets, and extraordinarily bad at making habitable ones. What we found out there in the dark when we finally had the eyes to see it was a catalogue of horror. Worlds where it rains liquid iron. Worlds where the wind moves at 8 times the speed of sound. Worlds where entire atmospheres are being peeled away by their stars like the skin off a grape. Worlds tidally locked into permanent day and permanent night, split down the middle by a razor-thin line where something, maybe, could survive. We went out looking for Earth's twin. What we mostly found was its nightmares, and that, right there, is the story we're going to tell tonight. The first confirmed exoplanet orbiting a sun-like star was discovered in 1995 by Swiss astronomers Michel Mayor and Didier Queloz, who would later share the Nobel Prize in Physics for their work. The planet they found was called 51 Pegasi b, and it was already deeply, immediately strange. It is a gas giant, roughly half the mass of Jupiter, but it orbits its star in just 4 days. 4 days. For context, Mercury, the closest planet to our Sun, takes 88 days to complete one orbit. 51 Pegasi b whips around its host star at a distance that should not, according to the model scientists had at the time, even be possible for a gas giant to exist. Before this discovery, the prevailing theory of planet formation held that large gas planets had to form far from their stars, in the cold outer regions of a solar system where the raw materials of ice and gas are abundant. The idea that one could exist hugging its star so tightly was not just unexpected. It required scientists to completely rethink how planetary systems form and evolve. Maybe planets migrate inward after they form. Maybe the early solar system is a far more turbulent, dynamic place than anyone had assumed. These are questions planetary scientists are still actively wrestling with today. But here is the thing that makes 51 Pegasi b worth noting, not just as a discovery, but as a warning. This was the very first planet we found around a sun-like star, and it was already so alien, so unlike anything in our solar system, that it reshuffled the scientific understanding of how planets work. If the very first one broke all the rules, what were the rest going to be like? The answer, it turned out, was even weirder. Over the next decade, as more exoplanets came in, a pattern emerged. The universe seemed to love what astronomers call hot Jupiters, massive gas giants sitting dangerously close to their stars, baking at temperatures that would vaporize most metals, whipping around in orbits that last hours or days instead of years. These planets had not shown up in our own solar system, so we'd assumed they were rare. They were not rare, they were everywhere. And they were alarming. Think about what it means to live on a moon of one of these hot Jupiters, if such a moon even existed. Your sky would be dominated by a gas giant so enormous it would fill the horizon. That gas giant would be so close to its star that its very atmosphere would be screaming. Temperatures would be high enough to melt rock. The radiation environment would be lethal many times over. It would be nothing like what we had imagined when we dreamed about finding other Earths. But the hot Jupiters were just the beginning. If you had to pick the single most cinematically horrifying exoplanet we've found, many astronomers would point you to WASP-76b without hesitation. WASP-76b sits about 640 light-years away from us, which sounds like a lot, but in galactic terms is practically next door. It is a gas giant, roughly the mass of Jupiter, but it orbits its star at a distance so close that 1 year there lasts less than 2 Earth days. Its day side, the face of the planet permanently locked toward its star, reaches temperatures above 4,000 degrees Fahrenheit. That is hotter than the surface of many stars. It is hot enough to vaporize iron, and that is exactly what happens. The iron in WASP-76b's atmosphere vaporizes on the day side, turning into a metallic gas that rides enormous planetary winds toward the night side. On the night side, temperatures are cooler, still several thousand degrees, but cooler. And when iron vapor hits cooler air, it does what any vapor does when it cools. It condenses, it forms droplets, it falls, it rains iron on WASP-76b, not metaphorically, not in some exotic astrophysical sense that barely resembles rain. It literally rains molten iron from the sky. Astronomers confirmed this in 2020 using an instrument called ESPRESSO on the Very Large Telescope in Chile. They detected a strong iron signal on the day side of WASP-76b and then watched that signal disappear on the night side, consistent with the iron condensing and falling out of the atmosphere before it could be detected. The night side of this planet, every single day of every single year since it formed, has been receiving a shower of liquid metal from above. There is something almost poetic about the fact that the first truly jaw-dropping exoplanet weather system we confirmed was not something abstract or distant. It was a planet raining iron. It sounds like something out of mythology, like a punishment handed down by some ancient god. But it is real. It is happening right now, 640 light-years away, and it has been happening for billions of years. WASP-76b is in a class of planets called ultra-hot Jupiters, and it is far from the only one we have found. These planets occupy a particularly extreme corner of the exoplanet catalogue, and they have been teaching us things about atmospheric chemistry that we could not have predicted. But if WASP-76b is horrifying for its weather, there is another planet nearby in the catalogue that is horrifying for a completely different reason. And this one looks, at first glance, almost familiar. You know what colour Earth looks from space? You've seen the images. That deep, rich, almost impossibly beautiful blue. The colour of oceans, the colour of atmosphere, the colour of a world that is alive. It is the most recognisable image humanity has ever produced. The pale blue dot. HD 189733b is blue. It is deep, vivid, saturated blue, and when astronomers first measured its colour in 2013, there was a moment, brief, wonderful, quickly corrected, of something that felt almost like recognition. A blue world. A world that looked, from a distance, like home. HD 189733b is 64 light-years away. It is a gas giant orbiting very close to an orange dwarf star. And that blue colour, it has nothing to do with oceans. It comes from silicate particles in the atmosphere, tiny grains of magnesium silicate, essentially the same stuff as talc, suspended in the upper layers of the planet's air. These particles scatter blue light the same way Earth's atmosphere scatters blue light. A completely different mechanism, producing the same beautiful, deeply misleading result. Here is what HD 189733b is actually like. The dayside temperature is around 1700 degrees Fahrenheit. The planet is tidally locked, meaning one face permanently points toward its star and the other is in eternal darkness. The temperature difference between the two sides drives winds that have been measured at approximately 5,400 miles per hour. That is more than 7 times the speed of sound. The fastest surface wind ever recorded on Earth was 253 miles per hour during a tropical cyclone in Australia. On HD 189733b, that would be a gentle breeze. The wind there is so violent that it wraps the entire planet in a perpetual roar, pushing heat and chemistry around at speeds that should not be possible in an atmosphere. And those silicate particles, the ones responsible for the beautiful blue colour, are not just floating peacefully in the air. They are being driven horizontally by those 5,000 mile per hour winds. They are effectively glass. And they are falling sideways through the atmosphere as the wind howls in a constant lateral rain of hot, tiny shards of glassy material. It is not just raining on HD 189733b, it is raining glass, sideways, at supersonic speeds, If you were somehow transported to HD 189733b, you would not see a beautiful blue world. You would be immediately vaporized by the heat, shredded by the wind, and sandblasted by glass before you had time to appreciate the colour. The beauty of this planet, visible only from the safety of 64 light-years away, is entirely lethal up close. Astronomers actually love HD 189733b for exactly this reason. Not because they want to visit it, but because it is so extreme that studying it teaches them about atmospheric dynamics in conditions they would never see in our solar system. The planet has been observed by both Hubble and Spitzer, and later by Webb, and it keeps producing new surprises about how heat moves through a planetary atmosphere, how chemistry changes under such radical conditions, and what the spectrum of light from a catastrophically hostile world actually looks like. In a way, HD 189733b is the kind of planet that makes planetary science as a field enormously richer, even as it makes any hope of finding life there vanish immediately. There is a planet in our galaxy that, depending on the day, is hotter than most stars. Kelt 9b is its name, and it holds the record for the highest dayside temperature of any known exoplanet, sitting at somewhere around 9,000 degrees Fahrenheit on its sun-facing side. To give that number some meaning, the surface of our Sun is about 10,000 degrees Fahrenheit. Kelt 9b's dayside is genuinely approaching stellar surface temperatures. It is not a star, it lacks the mass to trigger nuclear fusion, but in terms of sheer heat, it occupies territory that most stars would recognise. The reason for this is the star it orbits. Kelt 9 is itself an exceptionally hot star, nearly twice the size of our Sun and nearly twice as hot. It belongs to a class called A-type stars, which burn with a blue-white intensity that our own yellow Sun cannot match. Kelt 9b orbits this already scorching star at a distance that makes WASP 76b's orbit look spacious by comparison. It completes one orbit in just under 36 hours. It is tidally locked, so one face perpetually receives that stellar blaze, while the other sits in comparative cold, though even the night side is still thousands of degrees. What KELT 9b's extreme temperatures actually do to its atmosphere is something remarkable and strange. Molecules cannot survive at these temperatures. The heat is so intense that it breaks apart the chemical bonds that hold molecules together. Water cannot exist as water. It gets ripped into hydrogen and oxygen atoms. Carbon dioxide, methane, all the atmospheric gases we associate with planets, they simply cannot hold themselves together in Kelt 9b's atmosphere. Instead, the planet's atmosphere is made up of free individual atoms and simple ions, stripped of their molecular partners. It is, in a chemical sense, more like a stellar atmosphere than a planetary one. And then there is what the star is doing to the planet over time. KELT 9b is losing mass. The stellar radiation is stripping the planet's atmosphere away, launching it into space. This process, called photoevaporation, is happening to many close-in planets, but on Kelt 9b it is happening at a rate estimated to remove millions of tons of material per second. The planet is, very slowly, being eaten by its star. Over astronomical timescales, it will simply cease to be the planet it is today. What KELT 9b teaches us more than anything is about the limits of what the word planet can even mean. We tend to think of planets as stable, permanent things. Earth has been here for 4.5 billion years, and it will be here for billions more. Kelt 9b challenges that comfortable assumption. Planets are not permanent. Under the right circumstances, they can be destroyed from the outside in, their very substance boiling away into the void. The boundary between planet and evaporating gas cloud is not as clear as we once assumed. There is a place in our galaxy where 3 planets orbit a dead star, and astronomers sometimes describe it as one of the creepiest things in the known universe. A pulsar is what remains after a massive star dies in a supernova explosion, the most energetic event in the universe aside from the Big Bang itself. When a massive star's core collapses, it produces an object of incomprehensible density, a neutron star packing more mass than our entire Sun into a sphere roughly the size of a city. Some neutron stars spin incredibly fast, dozens or even hundreds of times per second, and as they spin, they emit beams of radiation that sweep through space like a lighthouse. These spinning, beaming neutron stars are called pulsars. In 1992, astronomers Alexander Wolszczan and Dale Frail announced the discovery of the first confirmed exoplanets ever found, and they were orbiting a pulsar. The system, designated PSRB 1257+12, contains at least 3 confirmed planets. By the standards of extrasolar science, this was a history-making moment. But the history was immediately profoundly uncomfortable. Think about what it means for a planet to orbit a pulsar. The pulsar is the remnant of a star that exploded. The explosion, the supernova, would have been catastrophic for anything that existed in that system beforehand. The shockwave would have stripped atmospheres, sterilized surfaces, vaporized oceans. If these planets existed before the supernova, they survived as scorched, stripped shells of whatever they once were. And if they formed after the supernova from the debris of the explosion itself, then they are made of the ash and fragments of a destroyed star, coalescing under the influence of a dead star's gravity. Either way, these planets orbit in an environment of constant, intense radiation. Pulsars emit enormous quantities of X-rays and high-energy particles with every rotation. The planets in the PSRB 1257+12 system are bathed in this radiation continuously, with no relief, no magnetic field strong enough to protect them, no atmosphere left to absorb and deflect the assault. They are ghost worlds, rocky bodies moving silently around a spinning stellar corpse, irradiated and dead, fossils of a system that may once have been alive. Astronomers sometimes refer to PSRB 1257+12 and its worlds as a graveyard. It is perhaps the most haunted address in the known galaxy, and it remains one of the most extreme environments, not because of heat or cold or wind, but because of what it represents, the aftermath of total stellar-scale destruction. A reminder that the universe is not always building. Sometimes it is tearing down. Pop culture has long been enchanted by the idea of a planet with 2 suns. The image of Luke Skywalker standing on Tatooine, watching a double sunset paint the sky in amber and gold, became one of the most iconic images in science fiction. It spoke to something deep. The idea that even in a galaxy far away, there could be peace and beauty and longing. 2 suns felt almost more romantic than one. Reality, as usual, had other plans. Kepler 16b is a real planet orbiting 2 real stars, about 250 light-years from Earth. It was discovered in 2011 by the Kepler telescope and generated enormous excitement, not least because it immediately drew Tatooine comparisons from everyone who heard about it. A planet with 2 suns, a circumbinary planet in the language of astronomers, orbiting both stars of a binary system rather than just one. And then the numbers came in. Kepler 16b is a gas giant, roughly comparable to Saturn in mass. Its surface temperature sits somewhere between -100 degrees Fahrenheit and -150 degrees Fahrenheit. It orbits at a distance where neither of its 2 stars provides enough warmth to push it into a remotely hospitable range. One of those stars is a red dwarf, the other a smaller orange star, and together they heat the planet to temperatures that would make Antarctica look like a Mediterranean vacation destination. There is no solid surface to stand on. because it is a gas giant. The temperatures are lethal to any chemistry we associate with life. The radiation environment from two stars is complex and unpredictable. The double sunset on Kepler 16b, if you could somehow survive long enough to watch it, would be genuinely spectacular. You would see two disks descending toward a horizon you could not stand on, painting the upper clouds of a frozen gas giant in colours that no human eye has ever processed in real life. It would be extraordinary. It would also be the last thing you ever saw, as you simultaneously froze to death and asphyxiated in an atmosphere of hydrogen and helium. The Tatooine fantasy is lovely. The reality of Kepler 16b is a reminder that nature does not owe us beauty and habitability in the same package. Sometimes it gives you the stunning double sunset. Sometimes it keeps the warmth for itself. Not every terrible exoplanet is terrible because of temperature or radiation or wind. Some are terrible because of what is happening to them right now, because they are in the process of being destroyed and the destruction is slow enough that we can study it. WASP-12b is perhaps the best example. It is a gas giant about 40% larger than Jupiter, orbiting its star at a distance of roughly 2 million miles. To compare that, Earth is about 93 million miles from the Sun. WASP-12b is so close to its star that it completes one orbit in just 26 hours. At that distance, the star's gravity is doing something extraordinary to the planet's shape. A planet's structural integrity depends on the balance between its own gravity, pulling it into a sphere, and the tidal forces of whatever bodies are pulling on it from outside. At 2 million miles from its star, WASP-12b has lost that balance catastrophically. The star's gravitational pull is so strong that it is distorting the planet out of its spherical shape, stretching it toward the star, elongating it into something closer to an egg. The planet's atmosphere is being funneled directly into the star in a continuous stream of gas and material. WASP-12b is being eaten. Not all at once, not dramatically, just quietly, persistently, year after year, the planet losing material into its host star in a slow planetary death that has been going on for billions of years and will continue until there is nothing left. Astronomers estimate the planet has perhaps 10 million years of existence remaining before the star has consumed enough of it to essentially end it as a recognizable world. 10 million years sounds like a long time from a human perspective. From a cosmic one, it is the blink of an eye. The planet is, on astronomical timescales, already almost gone. And here is the part that makes WASP-12b genuinely useful, scientifically. By watching a planet actively losing mass to its star, astronomers can directly study the process of planetary erosion, how atmospheres are lost, how material transfers between gravitational bodies, how the chemistry of a planet changes as its outer layers are stripped away. WASP-12b is, in a sense, giving astronomers a live tutorial on planetary destruction. It is an unfortunate planet but an invaluable teacher. There are others like it. GJ3470b, AU Microscopii b, and several others are all showing signs of atmospheric escape, their outer layers being driven off by radiation and stellar winds. In many cases, these planets are losing material so rapidly that you can almost think of them as deflating, very slowly, over millions of years. The universe, it turns out, does not just build planets, it also gradually takes them apart. Here is something that will rearrange the way you think about what a planet can be. Most planets in our solar system rotate freely. Earth takes 24 hours to spin once on its axis. Mars takes about 24.5 hours. Venus, famously, takes 243 Earth days. It rotates so slowly that a single Venusian day is longer than a Venusian year. But all of them rotate. The whole planet cycles through day and night, light and dark, warmth and cold. Many of the exoplanets we have found do not rotate like that. They are tidally locked to their stars, just as our moon is tidally locked to Earth, always showing us the same face. When a planet is tidally locked to its star, one side is in permanent daylight, the other in permanent night, and that arrangement never changes. There is no day-night cycle, there is just a permanent, unchanging split. The day side of a tidally locked planet in the habitable zone can be scorching. The star beats down on it without relief, without the moderation that comes from the planet rotating and distributing heat. The night side plunges into frozen darkness, temperatures dropping to hundreds of degrees below zero, in some cases freezing out the very atmosphere so it accumulates as frost on the cold hemisphere. Between these two extremes, there is a band that scientists sometimes call the terminator zone, or the twilight ring. It is the line between permanent day and permanent night, where the star is always on the horizon, where the light is always low and slanted and golden. This terminator zone has attracted serious scientific attention in recent years because it might actually be the most habitable part of a tidally locked planet. The temperature there is moderated between the two extremes. Depending on the atmosphere and the presence of water, the terminator zone could support liquid water, complex chemistry, and potentially life. It would be an unusual kind of habitability, permanently twilight with one side of your sky bright and hot and the other dark and cold, but it might be enough. Speculoos 2c, a planet about 106 light-years away, is one of the candidates for this kind of tidally locked habitability. It orbits a red dwarf star that is only about 15% the size of our Sun, and because the star is so small and cool, the habitable zone is very close in. The planet's year lasts just 8.5 Earth days. It is probably tidally locked. Its day side might be too hot, its night side might be too cold, but that ribbon of twilight running between them is an open question. Scientists genuinely do not know yet whether the terminator zone there could support life. They need more data, they need better telescopes, they need time. The fascinating thing about tidally locked planets is that they change the very question of what habitability means. We have always thought about habitability in terms of averages, average temperature, average radiation. But a tidally locked planet has no average. It has extremes coexisting side by side forever. Life there, if it exists, would be life adapted not to a moderate environment, but to a very specific narrow band within an otherwise hostile world. That is a radically different picture of what a living planet might look like. And there are a lot of these worlds out there. Red dwarf stars, the smallest, coolest, longest-lived stars in the galaxy, tend to have habitable zones that are close enough to the star that tidally locked planets are common, and red dwarfs are by far the most common type of star in the Milky Way, making up about 70% of all stars, which means that if you are statistically most likely to find life on another planet somewhere in this galaxy, that planet is probably orbiting a red dwarf. It is probably tidally locked. It probably has no day-night cycle, no seasons in the way we understand them. It lives in eternal twilight on one side and eternal midnight on the other. That is either wonderful or deeply strange depending on how you look at it. In 2017, astronomers announced the discovery of 7 Earth-sized planets orbiting a single red dwarf star 40 light-years from Earth. The star was called TRAPPIST-1, named after the telescope in Chile that first spotted the planets, and for a moment the whole scientific world caught its breath. 7 Earth-sized planets, around one star, 3 of them sitting in the habitable zone, the region where liquid water could theoretically exist on a rocky surface. At 40 light-years away, close enough that the James Webb Space Telescope, still being planned at the time, might actually be able to study their atmospheres. The TRAPPIST-1 system was, on paper, the best candidate for finding life elsewhere that had ever been identified. it generated headlines around the world. Scientists described it in terms that, for scientists, amount to barely contained excitement. Then the James Webb Space Telescope launched on Christmas Day of 2021 and began looking at the TRAPPIST-1 worlds in extraordinary detail. And what it found was more complicated than anyone had hoped. The innermost planet, TRAPPIST-1b, appears to be a bare rock. No detectable atmosphere, stripped clean by the star's radiation. TRAPPIST-1c, the second planet, also shows signs of having lost its original atmosphere or perhaps never developed a significant one. TRAPPIST-1d, the third, shows similar patterns. These are the planets closest to the star, and TRAPPIST-1, though small, is an active star. It flares. It sends bursts of X-rays and ultraviolet radiation washing over its planets in events that, for a world without a strong magnetic field, could be deeply damaging over billions of years. As of early 2026, Webb is still actively studying TRAPPIST-1e, the fourth planet, which sits in the middle of the habitable zone. Analysis of the first 4 observations of that planet has not yet found definitive signs of an atmosphere, but it has also not ruled one out. Scientists are conducting 15 additional observations using a clever technique where they observe both TRAPPIST-1b and TRAPPIST-1e at nearly the same time. Because Planet B appears to be a bare rock, any signals that show up uniquely during Planet E's transit can be attributed to its atmosphere rather than the star. It is painstaking, careful work. The signals they are looking for are tiny, a fraction of a percent of the star's total light, and the star itself is variable enough to complicate the measurements. What this means in practical terms is that the TRAPPIST-1 system, which was perhaps the greatest source of hope in the exoplanet field, is turning out to be more complicated and more sobering than the initial excitement suggested. The inner planets look unfavourable. The outer ones, E, F and G, are still being studied. The jury is very much still out. But the early results from Webb have introduced a note of caution into what was previously a story of pure possibility. Red dwarf stars, as beautiful and long-lived as they are, have a tendency to be energetically active, particularly when they are young. They flare, they send radiation, and for planets that need to develop and hold on to an atmosphere over billions of years, those early years of stellar violence may be enough to strip away the conditions needed for life before life ever gets a chance to start. This is not a closed case. Science rarely is. But it is a sobering reminder that finding a planet in the habitable zone is only the first step in a very long checklist. Sometimes the universe produces something so strange that the reaction from the scientific community is not excitement or awe, but genuine confusion. These are the planets that break the models, the worlds that, according to everything we thought we understood about how planets form and evolve, simply should not be there. WASP 193b, confirmed in 2023, is one of the most baffling objects in the current exoplanet catalogue. It is a gas giant, roughly 1.5 times the diameter of Jupiter, but its mass is only about 14% of Jupiter's mass. That means its density is roughly equivalent to cotton candy. Imagine a planet the size of Jupiter and a half, weighing almost nothing. It is so diffuse, so puffed up, that if you could somehow drop it in an ocean large enough to hold it, it would float, with room to spare. How does a planet become this way? Scientists genuinely do not know. The leading idea involves extreme stellar heating puffing up the atmosphere to enormous size, but the numbers for WASP 193b do not quite work out using the models currently available. The planet is more inflated than any model predicts it should be. It is, in the language of astronomers, anomalously fluffy. And that anomaly is scientifically valuable, because it means the current understanding of hot Jupiter physics is incomplete. WASP-193b is telling us that something is happening in these extreme environments that our models have not yet captured. Then there is TOI 6894b, announced in June 2025. This planet orbits a binary star system, two stars orbiting each other, and the planet orbits both of them together. But it is not just any circumbinary planet. The binary consists of two brown dwarfs, objects that are too massive to be planets, but too small to be full stars, occupying a strange in-between category of astronomical object. And the planet orbits this pair of brown dwarfs on a polar orbit, meaning its orbital path is tilted at nearly 90 degrees to the plane in which the brown dwarfs orbit each other. It loops over the top of both of them, like a hula hoop spinning sideways around two people standing back to back. Astronomers had theorized that such polar orbiting planets might exist, because we had found protoplanetary disks in polar orientations around binary stars. But finding an actual confirmed planet in this configuration was still startling. It means the geometry of planetary systems can be far more three-dimensional and complex than our solar system's nice, flat disk arrangement had led us to assume. Planets can form in orientations that, from Earth's perspective, look almost architecturally impossible. And these planets, the impossible ones, the cotton candy planets, the polar orbiting double brown dwarf companions, are not just curiosities. They are the data points at the edges of our understanding. They are the places where our models break and where new models need to grow to replace them. Every planet that should not exist, according to our current theories, is an invitation to think more carefully about what those theories are missing. Not every terrible exoplanet is terrible because of heat. The galaxy has plenty of frozen nightmares to offer alongside the burning ones. Ogle, 2005, BLG 390lb sits in a region of space that astronomers found using a technique called gravitational microlensing, a method that uses the way gravity bends light to detect planets that transit methods and radial velocity cannot easily reach. The planet was detected in 2005, and it is not close. It is found toward the centre of the galaxy, much further away than most Kepler or TESS planets. It is also extraordinarily cold. The average surface temperature is estimated at around -370 degrees Fahrenheit, roughly 50 Kelvin or 50 degrees above absolute zero. The temperature at which even the most resilient chemistry we know of would simply stop. Water, methane, carbon dioxide, everything that matters for life as we know it would be frozen solid on this world. There is no season that warms it. There is no greenhouse effect to speak of. It sits in the cold, dark outer reaches of its system, orbiting a small, dim star on a nearly 10-year orbit, accumulating frost and silence. It is sometimes called an ice ball, and that description is accurate in the most literal sense. It is not a frozen Earth. It is not a planet that was once warm and then cooled. It is simply a world that has always been cold, formed cold, stayed cold, and will remain cold for as long as its star keeps burning and probably long after. It represents a category of planet that may be common in the outer reaches of solar systems throughout the galaxy. Worlds with the right size, the right rocky composition, but positioned so far from any warmth that they have never had a chance at anything more than frozen geology. What OGLE 2005 BLG 390lb makes you appreciate is the extraordinary precision of Earth's position. Not just in the habitable zone, that is already remarkable, but in a habitable zone around a star of the right size and temperature, formed at the right time in the galaxy's history, with a magnetic field, a moon of the right size to stabilize its axial tilt, and enough internal heat to keep plate tectonics running for billions of years. The number of conditions that had to line up for Earth to be what it is, when you look at what the alternative worlds look like, starts to feel genuinely astonishing. Here is where the story takes a gentler turn for a while at least. Not everything we found in the search for Earth 2.0 was a nightmare. Among the thousands of exoplanets catalogued, a small number have attracted attention not for how hostile they are, but for how potentially hospitable they might be. And in some cases, scientists have begun to consider whether these worlds might actually be better than Earth for supporting life. Not just equivalent, better. This is the idea behind what astrobiologists call superhabitable planets. The concept, first formally laid out by researchers Renee Heller and John Armstrong in 2014, challenges a deeply human assumption that Earth is the gold standard for life. Earth is the only world we know to host life, so naturally we use it as the benchmark. But that logic has a flaw. Earth is the only world we know to host life because we cannot yet see the life on any other world. That does not mean Earth is the best possible environment for life. It might just mean Earth is the first one we happen to be born on. What would a superhabitable planet look like? The researchers identified several criteria. It would probably be slightly larger than Earth, perhaps 1 to 1.5 times Earth's mass. A more massive rocky planet retains internal heat longer, keeps plate tectonics active for more billions of years, and maintains a magnetic field that protects the surface from radiation. It would probably have more water than Earth, not too much, which would drown all the land and eliminate shallow coastal ecosystems, but somewhat more, creating an abundance of the shallow water environments where biodiversity tends to explode. It would probably orbit a K-dwarf star, a star slightly smaller and cooler than our Sun, with a lifespan of around 30 billion years, giving life far more time to evolve into complexity than our Sun's 10 billion year clock allows. It would probably be slightly warmer than Earth on average, perhaps 5 to 10 degrees Fahrenheit warmer, because warmer climates tend to support greater biodiversity. And it would probably be somewhat older than Earth, somewhere between 5 and 8 billion years old, giving complex life more time to develop. KOI 5715.01 is one candidate. It is about 3,000 light-years away, orbiting within the habitable zone of its star. The planetary system it belongs to may be around 5.5 billion years old, making it about 1 billion years older than our own solar system. It is larger than Earth, though possibly somewhat too large to perfectly fit the superhabitable profile. Its temperature might be cooler than ideal, but scientists have noted that with the right atmospheric composition, a greenhouse effect of the right strength, it could reach conditions favourable for life. It is a candidate, not a confirmed world. But it is worth knowing that it exists in the conversation. Kepler-69c sits about 2,700 light-years away and has been estimated to be around 7 billion years old, placing it squarely in the sweet spot of the superhabitable age range. It is a super-Earth, larger than our planet, orbiting in the habitable zone of a star. It might be too massive to be perfectly superhabitable, but its coastlines, if it has them, and the shallow ocean zones around any potential continents could be extraordinary places for life. And then there is LHS1140b, just 48 light-years away. In 2024, astronomers analysing data from the James Webb Space Telescope came to a striking conclusion about this world. It might be a Hycean planet, a class of worlds with deep hydrogen-rich atmospheres and vast liquid water oceans beneath. Or it might be a snowball Earth, entirely covered in ice. The measurements suggest it has an atmosphere of some kind, possibly a nitrogen-rich one. It is 1.7 times the size of Earth and 5.6 times its mass. It orbits in the habitable zone of its star, and it is close enough that Webb can actually study it in real detail. LHS1140b is not confirmed as habitable, but it is currently considered one of the most promising candidates in the entire exoplanet catalogue for for finding a world where liquid water, and possibly life, might exist. These worlds, the KOEs and the Keplers and the LHS candidates, remind us why the search continues despite all the horrors. For every iron-raining nightmare, for every glass storm gas giant, for every pulsar graveyard, there are whispers of something else out there. Something that might be almost right. Something that, with the right atmospheric chemistry and the right magnetic field and the right internal heat, might be almost home. Before we continue, it is worth pausing to understand what the James Webb Space Telescope actually changed about all of this, because the answer is almost everything. For decades, exoplanet science was fundamentally a science of detection. We could find planets. We could measure their sizes, their masses, their orbital periods. We could sometimes infer whether they were rocky or gaseous. But we could not, with any real precision, study what their atmospheres were made of. We could not look at the chemistry of a distant world and ask whether oxygen was present, whether methane was there, whether carbon dioxide or water vapour or any of the other gases we associate with life and habitability were in the air. The signal was too faint, the technology not quite sharp enough. Webb changed that. The telescope, orbiting the Sun at a distance of nearly 1 million miles from Earth, carries instruments of unprecedented infrared sensitivity. It can take the light that passes through a planet's atmosphere as it transits its star, spread that light into its component wavelengths, and read the absorption lines left by different atmospheric molecules, the way a musicologist reads sheet music. It can, in principle, detect gases present in quantities of parts per million in an atmosphere 90 light-years away. This is extraordinary. This is the kind of capability that makes the search for life elsewhere not just a scientific aspiration, but an active, current scientific program. The early results from Webb have been scientifically rich, and in many cases genuinely humbling. On WASP-39b, a hot Saturn orbiting a distant star, Webb detected carbon dioxide, sulfur dioxide, water and several other molecules in the first detailed exoplanet atmospheric spectroscopy of its kind. That result, published in 2022, was described by some astronomers as a watershed moment, proof of concept that atmospheric chemistry at this level of detail was now within reach. On K218b, a sub-Neptune orbiting a red dwarf about 120 light-years away, Webb found hints of molecules called dimethyl sulfide and dimethyl disulfide. These are significant because on Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton. It is a biosignature, a gas whose presence in an atmosphere would suggest biological activity. The word almost is doing a lot of work in that sentence. The signal was weak, not conclusive, and alternative non-biological explanations have not been ruled out. The scientific community responded with appropriate caution, but the fact that we can now detect tentative hints of potential biosignatures in the atmosphere of a planet over 100 light-years away is remarkable enough to deserve a moment of genuine appreciation. Webb is also teaching us hard lessons. On the TRAPPIST-1 system, the early results have been sobering rather than triumphant. The inner planets appear atmospherically bare. The habitable zone planets are still being studied. The star itself may be more problematic for its planets than originally hoped. These are not the results the community wanted, but they are the results the universe is providing, and dealing honestly with those results is what science is for. The Webb era of exoplanet science is right now in its early chapters. The telescope is expected to operate for at least 20 years, possibly longer. What it finds over that time will fundamentally reshape our understanding of how common habitable worlds are, what atmospheres on other planets actually look like, and whether the chemistry of life has found purchase anywhere other than here. We are, in a genuine sense, in the middle of the story, not at the end. Somewhere in all of this, in the iron rain and the glass storms and the tidally locked ghost worlds and the superhabitable candidates and the Webb spectra, there is a question that keeps surfacing, and it is worth sitting with it for a moment. What are we actually looking for when we search for Earth 2.0? The phrase itself implies something specific. A twin, a copy, a world with blue skies and green land and liquid oceans and a 24-hour day and seasons and a yellow sun and a moon of the right size. A world where, if you landed on it, you might almost feel at home. That is the dream encoded in the name. Earth 2.0, version upgrade. But the more we learn about other worlds, the more that picture starts to look like a very particular, very local fantasy. Earth is the reference point not because it is the best possible world for life, but because it is the only world for life that we have ever known. Our idea of what a habitable planet looks like is shaped entirely by a sample size of 1. The universe does not know about that sample size. The universe has been building planets for 10 billion years using a staggering variety of physical processes, and it has produced an ecosystem of worlds so diverse that our solar system, with its 8 tidy planets, is probably one of the calmer, more organised arrangements in existence. Out there are planets orbiting dead stars, planets orbiting 2 stars, planets orbiting no star at all, rogue planets wandering the galaxy in cold darkness with no sun whatsoever. There are planets made mostly of diamond, planets made mostly of water, planets with sulfuric acid for clouds and winds that never stop for billions of years. In all of that diversity, something has probably found a way to be alive. That is the quiet conviction that drives the people doing this work, not because the mathematics demands it. The mathematics of life's origin are still poorly understood enough that you could argue either way, but because the sheer scale of the universe, combined with what we know about chemistry and physics, and the robustness of life even here on Earth in its most extreme forms, makes it hard to believe that the universe made all this room and filled none of it but here. Tardigrades survive the vacuum of space. Bacteria have been found living in hot springs at nearly boiling temperatures, in the hyperacidic drainage of mine shafts, in the permanent ice of Antarctic lakes, in sediments miles below the ocean floor. Life on Earth, once it got started, turned out to be extraordinarily tenacious. It colonized every chemical niche, every physical extreme, every margin. If life elsewhere is anything like life here in its adaptability, and we have no reason to assume it is not, and some theoretical reasons to assume it might be, then the range of environments that could host it is much wider than a tidy little planet in a tidy little habitable zone. So maybe the horrible exoplanets, the WASP-76bs and the HD 189733bs and the pulsar graveyard worlds are not entirely hopeless. Maybe they are just hostile to the specific kind of life we know. Maybe, in the crushing pressure deep beneath a hot Jupiter's cloud layers, or in the Terminator twilight of a tidally locked super-Earth, or in some chemical process we have not yet imagined, something is alive right now in a way we would not recognize. That is not a scientific claim. That is imagination, running slightly ahead of data, the way it is supposed to. But it is grounded in what we know about life's tenacity, and it is, in a quiet way, one of the more hopeful thoughts available to us as we look at the catalogue of horrors we have assembled. The search for Earth 2.0, or for whatever the universe's version of a living world turns out to look like, does not end with James Webb. Webb is an extraordinary tool, but it has limitations. It cannot directly image small rocky planets around sun-like stars. It can study atmospheres through transmission spectroscopy, but the host stars need to cooperate, and many of the most interesting candidates orbit stars that complicate the signal in various ways. Webb opened a door. What comes next will walk through it. NASA is in the planning stages of a mission called the Habitable Worlds Observatory, which would specifically target Earth-like planets around Sun-like stars, the category of world that Webb finds difficult to study. The concept, still in development, involves a large space telescope with a coronagraph, an instrument designed to block out the glare of a star while imaging the much fainter planet beside it. This technology, called direct imaging, would allow astronomers to actually take pictures of Earth-like planets around nearby stars and analyse the light reflected from their surfaces. Instead of looking at starlight filtered through an atmosphere, they would be looking at the planet's own reflected light directly. The scientific potential of that capability is hard to overstate. There is also the Breakthrough Starshot initiative, which takes a completely different approach. Rather than building larger telescopes, Starshot proposes to send tiny spacecraft, essentially laser-propelled chips carrying cameras and instruments, to nearby star systems. The target is Alpha Centauri, our closest stellar neighbour, roughly 4 light-years away. The proposal calls for using enormous ground-based lasers to accelerate these chips to 20% of the speed of light, which would get them to Alpha Centauri in about 20 years. They would fly through the system, capturing images and data, and beam that information back to Earth. Whether Starshot is feasible, whether the engineering challenges can be solved, whether the data returned would be useful, these are all open questions. But the ambition it represents is worth noting. We are in a period of scientific history where, for the first time, the idea of actually travelling to another star system and looking at the planets there is being taken seriously as an engineering problem, rather than just a science fiction premise. And ground-based observatories are getting better too. The extremely large telescope currently under construction in Chile, with its nearly 40-metre primary mirror, will be capable of directly imaging large exoplanets around nearby stars when it begins operations. The 30-metre telescope, another enormous ground-based observatory in development, will extend those capabilities further. The tools are being built. The methods are being refined. The catalogue is growing every year. What this all adds up to is a trajectory, a curve of capability that started with the barely there Doppler wobble detections of the 1990s, passed through the Kepler revolution of the 2010s, entered the Webb era in the 2020s, and is now heading towards something that our generation may actually live to see. Within the next 20 to 30 years, we will likely know whether any of the nearby rocky planets in habitable zones have atmospheres consistent with biology. We may not be able to say definitively that life is there, but we may be able to say that something biological might be there, and the evidence is strong enough to warrant deeper investigation. That is not the dramatic announcement people have imagined for decades, but it is the way real science tends to work, not in sudden revelations, but in gradually accumulating certainty, one careful measurement at a time. Among all the exoplanets discovered over the past 3 decades, there are a handful whose stories carry a particular kind of weight, not because of what they are, but because of how close we came to misunderstanding them, or missing them entirely. Proxima Centauri b is the most famous of these. Proxima Centauri is the closest star to our solar system, a red dwarf sitting just 4¼ light-years away. In 2016, astronomers announced the discovery of a planet orbiting it, Proxima b, with a mass similar to Earth's, orbiting in the habitable zone of the star. The response was enormous. The nearest star to our Sun has a potentially habitable planet. If you could travel at 10% of the speed of light, which nothing we have built can do but theoretically, you could be there in 42 years. By stellar exploration standards, it is practically around the corner. And then the problems started stacking up. Proxima Centauri is an extremely active red dwarf. It flares constantly and violently, sending bursts of X-ray and ultraviolet radiation washing over the planet's surface on a regular basis. Proxima b, if it is tidally locked as many scientists believe, has one side permanently exposed to that radiation. Whether it has a magnetic field strong enough to protect its surface is unknown. Whether it has an atmosphere at all, whether the flares have already stripped it away, is one of the central questions about the planet. Follow-up studies have been inconclusive, and the planet is too close to its star to be easily studied by current instruments. The discovery of Proxima b sent a wave of excitement through the scientific community and the public alike. It also sent a wave of careful reconsideration about what it means to find a planet in a habitable zone around an active star. The habitable zone calculation assumes a certain range of radiation. Stellar flares add a wildly unpredictable variable to that calculation. A planet that would be habitable around a quiet star may not be habitable around an active one, even if it sits at exactly the right distance. Proxima b has not been ruled out. It has not been confirmed as habitable either. It exists in that uncomfortable scientific space of genuine uncertainty, where the data so far do not definitively point in either direction. The planet is there. What it is like is still, in a real sense, an open question. And then there is K218b. When it was first discovered, it was classified as a sub-Neptune, a planet smaller than Neptune but still gassy, not a rocky world, not a place anyone paid much attention to as a habitability candidate. It sat in its file in the exoplanet catalogue, another data point in a growing list. Then astronomers looked at it again, with different questions in mind, and they realised that K218b could be a Hycean world, a planet with a hydrogen-rich atmosphere, liquid water beneath it, and potentially the chemistry to support life. Not life on a rocky surface, life in a deep, warm ocean beneath a thick atmospheric blanket. That realisation changed the entire status of the planet. From an unremarkable sub-Neptune, it became one of the most scientifically interesting objects in the nearby galaxy. Webb has now studied it multiple times, finding carbon-bearing molecules, possible hints of dimethyl sulfide, and a picture that is complicated and fascinating and not yet fully resolved. K218b may be the most important planet we've found, or it may turn out to have a perfectly mundane, non-biological explanation for everything Webb has detected. We do not know yet, but the lesson it teaches is valuable regardless. The planet we almost overlooked may be the planet that matters most. That is a pattern worth remembering. In a catalogue of thousands, the worlds most worth our attention may not be the ones that announce themselves with spectacular extremes. They may be the ones sitting quietly in the middle of the list, waiting for someone to look at them with better tools and better questions. There is a particular challenge at the heart of exoplanet science that does not get talked about enough, and it is worth spending some time with. The challenge is this: the universe does not speak our language. When we look at the spectrum of light coming from an exoplanet atmosphere, we're not reading a readout. We're interpreting a signal that passes through multiple layers of complexity: stellar variability, instrument calibration, atmospheric modelling assumptions, quantum chemistry, before it becomes a number on a graph. Two different teams of astronomers looking at exactly the same Webb data can reach different conclusions about what it means. This is not a flaw in the science. It is the nature of working at the absolute edge of what our instruments can detect. The TRAPPIST-1 results have illustrated this beautifully. Early measurements of TRAPPIST-1c seem to suggest very little or no atmosphere, but astronomers have been careful to note that the absence of a detected atmosphere is not the same as the confirmed absence of an atmosphere. Some types of atmospheres, particularly thin or carbon dioxide-dominated ones, might produce a signal that current Webb observations could not detect or would misinterpret. The planet's silence in the data could mean it is bare rock, or it could mean the atmosphere is a type we are not yet able to see clearly with current techniques. Those are very different statements, and distinguishing between them requires more observations, better models, and continued refinement of the data analysis methods. This is the slow, careful, sometimes frustrating reality of doing real science in a new field. The history of astronomy is full of moments where our initial interpretation of data had to be revised as methods improved. The discovery that the universe was expanding, one of the most profound scientific revelations of the 20th century, was resisted, debated, and refined over years before the community reached consensus. The realization that black holes actually exist, that they are not just mathematical abstractions, took decades of accumulating evidence to become settled. The search for life on other planets will almost certainly follow a similar pattern. Tentative signals, careful skepticism, repeated observations, refined models, and gradually building confidence. Which means that anyone telling you definitively right now that we have found life, or definitively that we have not, is either overstating the evidence or underselling the difficulty of the problem. The honest answer, at the current moment, is that we're in the middle of the most careful and consequential investigation in the history of science, and the results are genuinely not yet in. Here is a question that scientists and philosophers and science communicators have thought about for a very long time, and that still does not have a settled answer. What actually happens to science, to society, to the human sense of self, on the day we find evidence of life elsewhere? The most likely scenario, given where the science currently stands, is not a dramatic announcement of confirmed alien civilization. It is more likely to be a gradual, tentative, carefully caveated result from a space telescope. A spectroscopic signature in an exoplanet atmosphere that is consistent with biological processes and inconsistent with all known non-biological explanations, but not impossible to explain away, and requiring extensive follow-up before the scientific community reaches consensus. That is a very different thing from a radio signal from the stars. It is a chemical measurement, interpreted through models, published in a peer-reviewed journal, debated at conferences, refined over months or years until either the evidence strengthens or an alternative explanation emerges. It will almost certainly not have a single dramatic moment. It will have a gradual dawning. And yet, even in that gradual form, the implications would be transformative. If the atmospheric chemistry of a planet 100 light-years away contains a gas that can only be produced by living things, if that result holds up under scrutiny, if it is confirmed by independent observations, if the scientific community reaches a consensus that the most parsimonious explanation is biology, then something fundamental about the human story changes. We would know for the first time that we are not alone, not in the sense of intelligent life-sending radio signals that might still be unknown, but in the sense that the chemistry of life, the basic project of self-replicating organised matter, has established itself in at least 2 places in the universe, which would make it unlikely to be limited to just 2, which would change the entire probability calculation for how common life is. It would also raise, immediately and urgently, the question of what kind of life is there? Microbes in an ocean, multicellular organisms, something with photosynthesis, something producing gases through metabolic processes we have not yet catalogued. The detection of a biosignature does not tell you much about what kind of life is doing the biosigning. It just tells you that something is alive, and that something is enough to rewrite astronomy, biology, philosophy, and the fundamental human question of whether we are special. Step back for a moment, all the way back, and look at what we've built in the span of just 30 years. In 1995, we confirmed the first planet orbiting a Sun-like star. 30 years later, we have over 5,800 confirmed exoplanets. We know the composition of the atmospheres of some of them. We know they come in varieties that our own solar system never hinted at. Cotton candy planets and iron rain worlds and tidally locked twilight zones and ghost worlds orbiting dead stars. We have a telescope in space right now actively studying the atmospheres of Earth-sized planets in habitable zones 48 light-years away. We're seeing hints of chemistry in those atmospheres that would be genuinely exciting if it were not for the very appropriate caution with which the scientific community is approaching the results. And we still have not found Earth 2.0. That is the honest statement. In 30 years of searching, with the most sophisticated equipment ever built for the purpose, we have not found a world we can say with confidence is like our own in the ways that matter, rocky, in the right temperature range, with liquid water on its surface, with an atmosphere we could breathe, with a star that is not trying to strip that atmosphere away. We have found candidates, we have found possibilities, we have found worlds that might, with the right conditions we cannot yet confirm, be places where life could exist. But Earth 2.0, the real one, the confirmed one, the one where we know, is still out there somewhere, not yet definitively in hand. That is not a failure, that is the situation. And the situation is, by any historical standard, remarkable. 30 years ago, we could not confirm any exoplanet. Today we have thousands, and a telescope that can taste their atmospheres. The pace of discovery in this field has been exponential, and there is no reason to believe it has reached its limit. The horrible exoplanets we found along the way, WASP-76b and its iron storms, HD 189733b and its glass rain, KELT-9b burning at stellar temperatures, the pulsar graveyard, the tidally locked twilight worlds, the cotton candy planets, and the disintegrating ones, are not disappointments. They are the universe showing us the full range of what it can make. They are the data that tells us how unusual, how specific, how genuinely improbable Earth's combination of conditions is. They are the context that makes the eventual discovery of something truly Earth-like, if it comes, so meaningful. Because every horrible world narrows the probability space. Every planet that fails to be habitable in a new and creative way tells us something about what habitability actually requires. Every iron-raining gas giant, every frozen ice ball, every atmosphere-stripped bare rock is a data point that refines our understanding of the very narrow window in which life like ours can exist, and by extension, expands our appreciation for the astonishing luck, or design, or statistical improbability, however you prefer to frame it, that put us here. The numbers in this story are so large that they tend to slide off the surface of ordinary comprehension. Hundreds of light years, thousands of light years, billions of years, temperatures of thousands of degrees, winds of thousands of miles per hour. The brain simply cannot hold these numbers in the way it holds the distance to the grocery store or the temperature outside this morning. They become abstract, placeholders for vastness rather than genuine understandings of it. So let us try something smaller. Let us try to feel, just for a moment, what 1 light year actually is. 1 light year is the distance light travels in a year. Light moves at about 186,000 miles per second. In 1 second, a beam of light travels far enough to circle the entire Earth about 7.5 times. In 1 year, that beam of light covers about 5.9 trillion miles. If you drove a car at 60 miles per hour, without stopping continuously, it would take you about 11 million years to travel 1 light year. HD 189733b, the beautiful blue planet with glass rain and supersonic winds, is about 64 light years away. That is approximately 700 trillion miles. Proxima Centauri b, the nearest potentially habitable exoplanet, is about 4.25 light-years away, still 25 trillion miles. These distances are not just large. They are, by the measure of any technology we currently possess or are close to developing, essentially impassable within a human lifetime. We are not going to visit these worlds, not us, not our children, perhaps not our civilization for hundreds or thousands of years, if ever. The exoplanets in this story are not destinations we will reach. They are signals we can receive, data we can analyze, atmospheres we can taste from afar with instruments of extraordinary sensitivity. They are known to us in the way that ancient sailors knew distant coastlines, from the behaviour of the currents and the patterns of birds in the sky, without having set foot there, without having touched the land. And yet they are known. That is the quiet miracle here. Those distant worlds are known to us. We have measured their masses and their sizes and their temperatures and their orbital periods, and increasingly the chemistry of their atmospheres. We know things about planets that our ancestors could not have imagined knowing without standing on them. We know about the iron rain. We know about the glass storms. We know about the Terminator twilight zones and the pulsar graveyard and the cotton candy planets. We know all of this from here, from this small, wet, extraordinarily lucky world, using instruments built from mathematics and silicon and ambition. That is extraordinary. That deserves to be said directly and without qualification. What human beings have done in the last 30 years of exoplanet science is extraordinary. The catalogue of known exoplanets will keep growing. The TESS mission continues its survey of the sky, adding candidates that ground-based and space-based follow-up missions then confirm. Webb continues its atmospheric studies, accumulating data on dozens of planets in its observing queue. New ground-based telescopes are coming online. New space missions are being designed. The Habitable Worlds Observatory, currently in the planning and proposal stage at NASA, represents the next major leap. A space telescope specifically designed to find and characterize Earth-like planets around Sun-like stars. It would use direct imaging rather than transit spectroscopy, looking at the reflected starlight from rocky planets rather than waiting for them to cross in front of their stars. It would be able to study planets that TESS and Kepler and even Webb cannot easily access. If funded and built on the timeline currently being discussed, it could be operational in the 2040s. That is within the lifetime of most people reading this or listening now. Within the 2040s, we might have a telescope capable of actually imaging nearby Earth-like planets and analysing their reflected light. We might be looking at spectra from worlds just like ours, or almost like ours, or very much not like ours but interesting in their own ways. We might, within the 2040s, have the first genuinely strong evidence for or against the existence of life elsewhere. That is not a guarantee. Science does not deal in guarantees, but it is a timeline that is grounded in the actual pace of development in this field, the actual capabilities of technologies currently being developed, and the actual resources being directed toward this problem. It is a real possibility, not a dream. And in the meantime, every piece of data from Webb, every new planet confirmed by TESS, every atmospheric spectrum that gets published and debated and refined is moving that timeline forward. The search has a momentum now that it did not have even 10 years ago. The scientific community working on this is larger, better equipped, and more focused than at any point in history. The horrible exoplanets will keep coming too. Every new catalogue update contains its share of gas giants, orbiting impossibly close to their stars, ice balls in the frozen dark, worlds with climates that would end any life we know of before it got started. They will keep teaching us. They will keep narrowing the window. They will keep making us grateful for the specific, improbable, fragile miracle of this particular planet, at this particular distance from this particular star, at this particular moment in geological and cosmic time. From space, Earth's atmosphere is visible as a thin blue haze around the edge of the planet. When you see photographs taken by astronauts on the International Space Station, you can sometimes catch it, a gossamer layer clinging to the surface, barely perceptible against the black of space. The atmosphere that makes all life on this planet possible is, in planetary terms, thinner than the skin of an apple. That thin blue line is what the James Webb Space Telescope is trying to detect on other worlds, a signal so faint that it amounts to less than a fraction of a percent of a distant star's light. A signal that has to be coaxed out of observations lasting hundreds of hours. A signal that carries the chemical fingerprints of whether a planet has water, carbon dioxide, oxygen, methane, the molecules that, in the right combinations, spell life. It is humbling, in the deeper sense, to think about what this means. The question of whether we are alone in the universe, one of the oldest, most profound questions the human mind has ever asked, is now being answered through the analysis of a tiny dip in a light curve, a slight absorption feature in a spectroscopic measurement, a pattern in data that requires sophisticated machine learning algorithms and theoretical models and years of careful work to interpret. The question is cosmic, the evidence is minuscule, and in between, holding the two together, is the extraordinary, improbable, continuing achievement of human science. There is a technique, speculative but scientifically grounded, that some researchers have proposed for detecting signs of civilization, rather than just life, on other worlds. It is called technosignature detection, and it involves looking not for biological gases but for the chemical byproducts of industry. Nitrogen dioxide, for instance, is produced both by lightning and by industrial combustion. The ratio of nitrogen dioxide in an atmosphere, more than lightning alone could explain in the right configuration, could theoretically indicate industrial activity. Chlorofluorocarbons, which have no natural source, would be a particularly strong signal of an industrial civilization. The SETI Institute has been searching for radio signals from other civilizations since the 1960s. So far, no confirmed signal has been found. The famous "wow" signal, detected in 1977 at the Big Ear Radio Telescope at Ohio State University, remains an unexplained narrow-band signal at the hydrogen frequency. The frequency SETI scientists chose as the most logical one for interstellar communication, because hydrogen is the most common element in the universe. It was never repeated, never confirmed, never explained. It was, for 37 seconds, the most interesting thing in the history of radio astronomy, and then it was gone. The search for radio signals from civilizations continues, with increasingly powerful equipment and broader frequency ranges. The question of why we have not heard anything, the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked at lunch in 1950, "Where is everybody?" remains unresolved. If intelligent civilizations are common in the galaxy, where are the signals? If they are not common, why not? Either answer is profound. The exoplanet work does not directly answer the Fermi paradox, but it does provide context. The more we learn about how hard it is to be habitable, how many specific conditions need to align, how aggressively stellar environments can strip away atmospheres, how narrow the window for complex life might be, the more the silence of the galaxy starts to feel less like an absence of life and more like a reflection of life's difficulty. Not impossible, not non-existent, but rare perhaps in ways that the size of the galaxy can partially mask. Even if intelligent civilizations occur on 1 in a million habitable planets, and 1 in a million rocky planets is habitable, there could still be thousands of civilizations in the Milky Way. Or there could be one. We are one. Right now, that is what we know for certain. Let the catalogue of horrible exoplanets settle for a moment. Let the iron rain on WASP 76 B fall in silence somewhere 640 light-years away. Let the glass storms on HD 189733b howl across that beautiful lethal blue sky. Let the pulsar at PSRB 1257+12 spin its quiet radiation over dead worlds that never knew what warmth was. Let Kepler 16b hang in the cold dark between its two insufficient suns. Let all of those worlds be what they are: extraordinary, alien, incomprehensible in their specificity, valuable in their strangeness, and quietly useful in what they teach us about the precision required to make a place like home. Because here, on this particular world, with its particular atmosphere and its particular magnetic field, and its particular moon holding its axial tilt steady over millions of years, something happened that has not yet been confirmed to have happened anywhere else. The chemistry organized itself. Life began, impossibly, from somewhere in the vast space between dead chemistry and living process. It diversified over billions of years into forms of staggering complexity and variety. And eventually, among all the living things that the chemistry produced, one kind of animal developed the ability to look up at the sky, recognize the points of light as distant suns, invent the mathematics to describe their behavior, build the instruments to detect the planets around them, and begin to ask, with genuine, rigorous, structured scientific seriousness, whether any of those planets might be home to something like itself. That is an extraordinary chain of events. The fact that it happened at all, given how hostile the universe demonstrably is to the conditions needed for it, is not something that should be allowed to become ordinary through familiarity. We are the universe looking at itself. We are the thing that the chemistry produced that can now study the chemistry. And we are doing it, right now, with Webb looking at TRAPPIST-1e, with TESS finding new planets, with theorists refining models and observers booking telescope time, and engineers designing the Habitable Worlds Observatory. We are right now in the middle of the most ambitious investigation our species has ever undertaken. Among the thousands of confirmed exoplanets, there is an absence worth noting. We have found very few planets that are truly similar to Earth in all the ways that matter. This is partly a selection effect. The methods we use are better at detecting large planets close to their stars than small rocky ones at Earth-like distances. But it is also a genuine reflection of how specific Earth's configuration is. The forthcoming Habitable Worlds Observatory is designed specifically to address this gap. Its coronagraph would block stellar glare with enough precision to image Earth-sized planets in the habitable zones of nearby Sun-like stars. The nearby stars, within about 30 light-years, include several that are candidates for hosting Earth-like worlds. Tau Ceti, a G-type star about 12 light-years away, with several planetary candidates including some in its habitable zone. Epsilon Eridani, a K-type star 10 light-years away. Alpha Centauri A and B, about 4¼ light-years away, in the same system as Proxima Centauri. 61 Cygni, Eta Cassiopeia. These are stars that we can see with the naked eye on a clear night. The planets that might orbit them, if they exist, if they are rocky, if they are in the habitable zone, are invisible to us now. In 20 or 30 years, we might be looking at their reflected light through an instrument not yet built, reading the chemistry of their atmospheres and asking, with data in hand, whether the thin blue line around them looks anything like ours. That is the trajectory of this search, from confirmation that planets exist, to understanding what they are made of, to reading what their atmospheres contain, to asking whether any of those atmospheres bear the signature of life. Each step requires better instruments. Each step builds on the one before. Each step is being taken right now by scientists who have chosen to spend their careers on one of the most important questions the human species has ever posed. return one last time to the horrible exoplanets, the ones that open this story, the ones that were supposed to be the nightmare catalogue, the universe's hall of horrors, the terrible things we found when we went looking for somewhere better. Here is what they actually are. They are teachers. WASP 76b and its iron rain teaches us about atmospheric dynamics at extreme temperatures, about how gases behave, how heat moves, how chemistry changes when you push it beyond what our solar system ever produced. That knowledge is foundational for understanding what a habitable atmosphere looks like by comparison. You cannot know what normal is if you do not know what extreme is. When planetary scientists build computer models of how Earth's atmosphere behaves, how heat circulates, how weather systems form, how greenhouse gases trap energy, they test those models against extreme cases. WASP 76b is an extreme case. The fact that iron behaves in its atmosphere the way water behaves in ours, evaporating on the hot side, condensing on the cool side, falling as precipitation, is not just a spectacular piece of weather. It is a real-world validation of the physics of phase transitions under conditions that no Earth-based lab could reproduce. Every model that accurately predicts the iron rain on WASP 76b is a model we can trust a little more when we apply it to worlds closer to our own conditions. Science works by testing ideas at the edges. These planets are the edges. HD 189733b and its glass storms teaches us about the relationship between a planet's temperature gradient and its wind speeds, the physics of heat redistribution across a tidally locked world. That understanding is directly applicable to the TRAPPIST-1 planets, which are also likely tidally locked, and to every other red dwarf world we study. The 5,000 mile/hour winds on HD 189733b are not random. They are the predictable consequence of a specific temperature difference between the day side and the night side, combined with the planet's atmospheric composition and pressure. The equations that explain those winds are the same equations that would govern, scale down, the wind systems on a smaller, cooler, tidally locked rocky planet. If you want to know how wind moves on TRAPPIST-1e, you study it first on HD 189733b. The Nightmare Planet is the proving ground for the models that will eventually help us understand the candidate planet. That is not an accident. It is how physics works. It does not change its rules depending on whether a planet is habitable. The same equations govern the pleasant breeze of a spring afternoon in a temperate garden and the iron-laden howl of an ultra-hot Jupiter's night side. Understanding the extreme version is how you gain confidence in your understanding of the moderate version. Kelt 9b teaches us about what happens to an atmosphere at stellar temperatures, about photoevaporation, molecular dissociation, the boundary between planetary and stellar physics. It expands the definition of what a planet can be at the extreme end, which helps us understand where life becomes impossible and how far the conditions need to deviate before all hope is gone. But it teaches us something else as well, something quieter and more philosophical. KELT 9b exists. It is real. It is there right now, a planet so hot its molecules cannot hold together, losing mass to its star second by second in an orbit that lasts 36 hours, around a star that burns at temperatures our sun cannot reach. The universe made this. The same universe that made Earth. The same physics that governs the gentle circulation of warm ocean currents along a tropical coastline also governs the catastrophic atmospheric stripping of KELT 9b. There is a strange unity in that. The laws of physics are not selective. They do not apply gently in pleasant places and violently in horrible ones. They apply everywhere, consistently, and the results depend entirely on the initial conditions: the size of the star, the distance of the planet, the composition of the atmosphere, the age of the system. Change those initial conditions, and the same physics that makes Kelt 9b a nightmare makes Earth a paradise. That is the deepest lesson in the catalogue of horrible exoplanets, if you're willing to sit with it long enough. We did not earn our pleasant conditions. They emerge from a specific set of starting parameters governed by physics that does not care about outcomes. We are the result of conditions that happen to be right in a universe where conditions are usually not right, producing something that calls itself fortunate and goes looking for more. The pulsar worlds teach us about the violence of stellar death, about what survives and what does not when a star explodes, about the resilience of planetary systems even in the aftermath of catastrophe. The PSRB 1257 plus 12 planets, orbiting their dead and spinning stellar remnant, tell us that planet formation is robust enough to persist even through one of the most energetic events in the cosmos. A supernova destroys almost everything in its vicinity, and yet planets, or the material that becomes planets, survive or reform from the wreckage. That is a remarkable statement about the tenacity of the gravitational process that builds worlds. It also raises a question that planetary scientists find genuinely interesting. If planets can form from the debris of a stellar explosion, from the ashes of a catastrophic death, could any of the chemistry needed for life survive in that debris? Not the life itself. The supernova would sterilize anything that existed. But the organic molecules, the carbon compounds, the amino acid precursors that have been found in meteorites and interstellar clouds, could those building blocks be scattered by stellar explosions and deposited on new worlds forming from the wreckage? Could the death of one star system, in some extraordinary and very rare circumstance, seed the formation of another? These are not currently answerable questions, but they are questions that the pulsar worlds make possible to ask. And in science, asking the right question is often more important than having the answer. The tidally locked worlds teach us about the diversity of ways a planet can be organised, how the absence of a day-night cycle changes everything about climate and potential habitability. They are also, right now, the most common type of potentially habitable planet we can study, which means understanding them is not an exercise in cataloguing the strange, but a direct investigation into the most likely form that extraterrestrial life's home might take. If life exists elsewhere in this galaxy, the statistical weight of the evidence suggests it is most likely to be found on a tidally locked world orbiting a red dwarf. Not because those are the nicest environments, but because they are the most common ones. Red dwarfs make up about 70% of all stars. Their habitable zones are close to the star, which makes tidal locking likely, and their enormous lifespans, trillions of years compared to our Sun's 10 billion, mean that life in those systems has had vastly more time to develop. If we want to think clearly about where life is most likely to exist, rather than where we would most like it to exist, the tidally locked red dwarf system is the answer, and every horrible tidally locked world we study, every planet split between permanent day and permanent night, every world where the atmosphere is being blasted by stellar flares while one hemisphere bakes and the other freezes, teaches us something about the conditions that life would need to overcome or adapt to or exploit to exist in those places. The Terminator Zone. The subsurface ocean shielded by kilometers of rock. The chemical processes in a frozen nightside atmosphere that might, just might, support a form of chemistry we have not yet imagined. These possibilities emerge from studying the hostile versions, and all of them together, the entire population of exoplanets, from the most horrifying to the most promising, teach us the single most important lesson that 3 decades of exoplanet science has produced. Earth is specific. Earth is the product of a long, improbable chain of circumstances. Earth is not typical, and therefore, Earth is precious in a way that even the most enthusiastic environmentalist has probably not fully reckoned with. When you look at the alternatives, really look at them, with data and physics and chemistry, The thin blue atmosphere around this particular rocky world starts to look like the most valuable thing in the known universe. Not because it is beautiful, though it is. Not because it is ours, though it is that too. But because it is so far unique, and uniqueness in a universe that has been manufacturing exoplanets by the billions for 10 billion years and has not yet revealed a confirmed second example of genuine habitability, deserves a specific and serious kind of appreciation. There is a tendency, in popular science communication, to treat Earth's specialness as a reason for comfort. Look how lucky we are. Look at this beautiful, rare thing we inhabit, and that is not wrong, but it is incomplete. Because if Earth is as rare as the exoplanet catalogue suggests, if the specific combination of distance from star, planetary mass, magnetic field strength, atmospheric composition, liquid water abundance, geological activity and orbital stability that makes this planet what it is happens only in a very small fraction of the universe's rocky worlds, then the fragility of that rarity deserves as much attention as the wonder of it. The horrible exoplanets are not just teaching us about other worlds, they are teaching us what this world is by showing us what it is not. They are the negative space that defines the shape of home. Every iron rainstorm on WASP 76b is also, in a quiet way, a reminder of the morning rain on a temperate hillside here. Every glass-scoured sky on HD 189733b is also a reminder of the benign blue overhead. Every frozen stillness of OGLE 2005 BLG 390LB is also a reminder of the warmth of a particular afternoon, in a particular season, on a particular world that, against all the odds of a vast and often hostile universe, got the numbers right. That is what the catalogue of horrors is really for. Not to frighten, not to impress, but to calibrate. To give us the scale we need to appreciate what we have, and the scientific foundation we need to keep looking for more. The search continues tonight. Right now, as this is being heard, the James Webb Space Telescope is pointed at something in the sky, probably a planet, or a star with planets, or a system that might yield something important. The TESS satellite is scanning its portion of the sky for transits. Ground-based observatories in Chile and Hawaii and the Canary Islands are tracking stellar wobbles and atmospheric spectra, and all the faint signals that add up piece by piece to knowledge. Somewhere in that gathering data there might be the planet we have been looking for, somewhere in the next Webb observation cycle, or the one after, or 5 years from now or 20. There might be a spectrum that makes a room full of careful, skeptical scientists go very quiet, and then start asking each other whether they are seeing what they think they are seeing. There might be a dimethyl sulfide signal that holds up under months of follow-up. There might be an oxygen feature in a rocky planet's atmosphere that has no geological explanation. There might be something, or there might not. The universe is under no obligation to be obliging on any particular timeline. The silence so far, not confirmed silence, not proved silence, but the absence so far of a confirmed detection, could mean life is rare, could mean our methods are not yet sensitive enough, could mean we're looking in the wrong places, could mean we're looking for the wrong things. Science, at its best, holds all of these possibilities open and keeps gathering evidence slowly, carefully, without forcing the data to fit the wish. There is something worth saying about the people who do this work. The astronomers and planetary scientists and astrobiologists who spend their careers on the exoplanet question are, on balance, among the most patient professionals in any field of human endeavour. An observation campaign on a single planet with Webb might involve dozens of transits spread over months or years, with each individual observation yielding a signal so faint that only the accumulated sum of all of them will be interpretable. You book telescope time months in advance. You wait for the planet to transit. You spend hours collecting photons. You bring the data home and spend weeks or months reducing it, removing instrumental artifacts, correcting for stellar variability, running it through atmospheric retrieval models, and then you look at what you have and you write it up carefully and honestly, including all the uncertainties, including the alternative explanations you cannot yet rule out, and you submit it to a journal and it gets reviewed, and if it is accepted you present it at a conference, and other scientists ask hard questions about your methodology, and you go back and check your work again. This is science, not dramatic, not fast, not heroic in the cinematic sense, just careful, relentless, honest accumulation of evidence. It is being done right now by thousands of people on multiple continents and in space, and it is the most important investigation our species has collectively undertaken. What we do know is this: the galaxy contains hundreds of billions of stars. The average star has more than one planet. Rocky planets in habitable zones exist in numbers that, even conservatively estimated, run into the hundreds of millions across the Milky Way alone. The chemistry of carbon-based life is not exotic. Carbon is the fourth most abundant element in the universe, and the organic molecules from which life is built have been detected in interstellar space, in meteorites, in the dusty clouds where stars are being born. The conditions for life's ingredients to assemble are not rare. They are found throughout the galaxy, in molecular clouds, in stellar nurseries, in the asteroid belts and cometary halos of solar systems still forming. The question is not whether the raw materials are available. They clearly are in abundance. The question is whether the process that turns those raw materials into living chemistry happens readily, or rarely, or somewhere in between. And we genuinely do not know. The origin of life on Earth, the actual moment or process by which chemistry became biology, roughly 3.8 billion years ago, in conditions we can partially reconstruct but not fully understand, remains one of the deepest unsolved problems in all of science. We know it happened. We do not know how, not with the precision that would allow us to calculate how likely it is to happen elsewhere. That uncertainty propagates directly into every estimate of how many living worlds the galaxy might contain. Are there millions? Thousands? Dozens? Just one? The honest answer, supported by the current state of knowledge, is that we do not know. The range of scientifically defensible estimates spans from essentially zero other inhabited worlds to essentially every habitable world teeming with life. That is an astonishingly wide range of uncertainty for something so important. What exoplanet science is doing, year by year, planet by planet, spectrum by spectrum, is narrowing that range. It is not closing it. Not yet, maybe not for decades. But every planet studied, every atmosphere characterized, every Hycean world investigated, every tidally locked super-Earth analyzed, brings the range of that estimate a little tighter. The terrible planets narrow it from one direction by showing us how often the conditions are wrong. The promising planets narrow it from the other by showing us that the right conditions, while not common, are at least findable. And the ambiguous planets, the K218bs and the LHS1140bs and the TRAPPIST-1ES, are the ones doing the most active work on the boundary right now, telling us slowly and carefully what the right conditions actually look like from the outside. So tonight the telescopes are looking, and tomorrow they will look again, and the data will accumulate, one transit, one spectrum, one careful measurement at a time, until the picture is clear enough to say something definitive about whether the universe reserved the chemistry of life for just one wet, improbable, beautiful world in one ordinary arm of one spiral galaxy among 2 trillion, or whether it scattered that chemistry generously across the dark and let it find its own way to something alive. The search is real, the people doing it are real, the instruments are real and operational and pointed at the sky. And the question, the oldest, most human, most important question we have ever asked of the night is, for the first time in history, being answered with actual data rather than speculation. That is where we are, not at the end, barely past the beginning. On the long road through the catalogue of horrible worlds and hopeful ones, looking for the one that confirms what billions of years of cosmic history have been quietly setting up. The answer is out there. We just have not found it yet. But we are looking, always looking, with better eyes every year and more patience than the universe probably expected, from something that has only been asking the question for a few thousand years and answering it scientifically for 30. The search for Earth 2.0 is not over. It has barely begun. And tonight, somewhere in the cold dark above this planet, the Webb telescope is pointing at a star, and the star has a planet, and that planet is quietly doing whatever it does, whether it is raining iron or freezing everything solid, or cycling the chemistry of something alive through the currents of a hydrogen ocean. And in a year or 5 or 20, we will know a little more about what it is. And that small, hard-won addition to human knowledge will be added to everything that came before it, and the picture will be a little clearer, and the search will continue. It always continues. The universe is very old and very large. This is the observation that tends to sit heaviest when you have spent time thinking about exoplanets. Not the excitement of the discoveries, though that is real, but the sheer, slow, geological patience of it all. The stars we are observing have been burning for billions of years. The planets we are cataloguing have been orbiting for billions of years. The light that Webb collects from TRAPPIST-1e tonight left that star 40 years ago, when the telescope was not yet built, when the planet had not yet been discovered, when the question of its atmosphere had not yet been formulated. The universe does not wait for us to be ready. It just keeps going. And there is something in that fact worth resting in for a moment. The light you're receiving right now, not from a telescope, just from the ordinary sky on an ordinary night, is ancient. The stars visible to the naked eye from most locations on Earth range from just over 4 light-years away to several thousand light-years. The light arriving from even the nearest of them has been travelling for years. The light from the more distant ones has been travelling for centuries, for millennia. When you look at the night sky, you are not seeing the universe as it is. You're seeing the universe as it was, at a whole range of different times all at once. A layered fossil record of light stretching back through history. And in that layered ancient light, the planets are invisible. The exoplanets, all 5,800 plus of them in the current catalogue, cannot be seen with the naked eye. They're too small, too dark, too close to the overwhelming blaze of their host stars. You can look directly at TRAPPIST-1's position in the sky and see nothing. The 7 worlds orbiting it are utterly invisible to an unaided human eye. The iron rain of WASP-76b falls in a system you could not point to without a star chart and a good telescope. The glass storms of HD 189733b happen in a blue star that you might, on the clearest of nights from the darkest of locations, just barely glimpse as a faint smudge in the constellation Vulpecula. The whole catalogue of horrors and wonders that we have assembled over 3 decades of exoplanet science exists entirely outside the range of human senses. We cannot see these worlds, we cannot hear them, we cannot feel their heat or their cold or their impossible winds. We know about them only through instruments, through the mathematics that interprets the instruments, through the peer-reviewed papers that interpret the mathematics, through the science communicators and educators who translate the papers into language that the rest of us can follow. The entire knowledge we have of exoplanets is mediated, indirect, built from inference and calculation, and the trusting acceptance that the physics really does work the way the physicists say it does. That is a remarkable epistemological position to be in. We are absolutely confident that WASP-76b exists, that it rains iron, that its winds reach speeds of thousands of miles per hour. We are confident in these things not because any human being has been there, not because any sensor has physically touched the planet, but because the mathematics of light and gravity and chemistry, tested in laboratories, verified in our own solar system, checked against every independent measurement we can devise, gives us no reason to doubt the picture it produces. The confidence in these distant worlds is the same confidence we have in the physics that makes our satellites orbit, our GPS work, our nuclear reactors run, our MRI machines image. It is earned confidence, built from the most successful intellectual enterprise in human history. And that confidence is part of what makes the exoplanet story so extraordinary. We have extended the reach of human knowledge across hundreds and thousands of light years, not by travelling there, but by being smart. By developing the mathematics, building the instruments, training the algorithms, running the models, and thinking clearly enough about what the data means. That is what all of this is, at its core. It is what human intelligence, applied patiently and honestly to a good question, can actually accomplish. Earth keeps going too. This thin, fragile, astronomically improbable world keeps spinning, keeps its atmospheric blanket wrapped around it, keeps its liquid oceans and its living things and its radio telescopes and its space observatories and its quiet, persistent, species-wide hope that we're not alone. Think for a moment about what it means that this hope is species-wide. It is not the hope of astronomers only. It is not confined to scientists or philosophers or science fiction writers. Poll people on any continent, in any culture, with any level of formal education, and you will find that the question of whether there is life elsewhere in the universe is one that resonates with almost everyone who encounters it. Children ask it without prompting. Ancient civilizations built myths and cosmologies that grappled with versions of it. The feeling that the universe cannot have produced only one living world is not a scientific intuition. It is something deeper, something encoded in the way human minds relate to vastness and to loneliness and to the possibility of company. Scientists have now given that ancient human feeling a framework, a rigorous, mathematical, observationally grounded framework that takes the feeling seriously and asks what the evidence says. And the evidence says, we do not know yet, but we are getting closer. The evidence says the ingredients are there. The evidence says the conditions, while specific and demanding, are not impossible to meet. The evidence says that within a few decades, we may have the tools to look at the reflected light from a world orbiting a nearby star and tell whether anything there is alive. Whether we are alone or not, the search itself is one of the most worthwhile things our species has ever done. Not because of what we might find, though the finding would matter enormously, but because of what the searching requires of us. It requires honesty, the willingness to publish results that disappoint, to publish results that are ambiguous, to resist the urge to claim more than the data supports. It requires patience, the willingness to spend decades refining the same question rather than settling for a provisional answer. It requires imagination, the ability to consider that life might look nothing like us, might exist in environments we would call lethal, might be producing signals we have not yet thought to look for. And it requires humility, the recognition that a species that has existed for a few 100,000 years on a planet that has existed for 4.5 billion years, in a galaxy that has existed for 13 billion years, does not automatically know the shape and scale of the universe's inventory. The humility that exoplanet science demands is not a weakness, it is a clarification. It clarifies what we know, what we do not know, and what we are in the process of finding out. It clarifies the size of the question against the size of our current answers. And in that clarity, that honest, uncomfortable, deeply motivating clarity, there is something that functions very much like peace. Because here is the thing about the long night, the cosmic patience, the billions of years of stars burning and planets orbiting in silence before anything was alive to notice. All of that time was not wasted. It was the time required. Life on Earth needed almost 4 billion years to get from the first simple cells to anything complex. It needed another 500 million years after that to get from complex single cells to multicellular organisms, another several hundred million years to get from multicellular life to animals, with enough intelligence to ask questions about the universe. The timeline of life is slow by human standards, but it is not slow by stellar ones. A red dwarf star lives for trillions of years. If life in its systems follows a similar timeline to life on Earth, there is time, incomprehensible amounts of time, for it to develop, to become complex, to look up, to wonder. The horrible exoplanets are part of that humility. They are the universe reminding us that our expectations are local, our intuitions are shaped by experience, and the galaxy is full of things that our experience did not prepare us for. And sitting alongside the humility, not contradicting it but complementing it, is a kind of steady wonder at the fact that we are here at all, asking these questions, building these instruments, reaching across the light years with nothing but mathematics and patience, and the deep human refusal to accept that the night sky is empty. And somewhere in all of that, among the iron rain, and the glass storms, and the ghost worlds, and the tidally locked twilight zones, and the Hycean ocean planets, and the superhabitable candidates, and the still being studied spectra of a small planet orbiting a red dwarf 48 light-years away, there might be something alive, something that found its own narrow margin, something that made the Terminator zone work, or found warmth deep underground, or learned to filter the radiation of a too-active star, or developed chemistry we have not yet catalogued in an ocean we cannot yet see. Something patient and ancient and alive, the way life is always patient and ancient and alive when you look at it across the full breadth of geological time. Something that might, if the physics of information transmission and the patience of civilizations permits, be reaching outward in its own way, sending its own signals, or simply living its life in the margins of a difficult universe, having solved the same problem we solved here, the problem of persisting, of continuing, of turning raw chemistry into something that eats and breathes and reproduces, and eventually, if enough time passes and enough complexity accumulates, looks up and wonders, we have not found it yet. The horrible exoplanets remind us how hard finding it is likely to be. The promising ones remind us why we keep trying. And the long, patient, ongoing work of the telescopes and the scientists and the instruments pointed at the dark night sky is the clearest expression our species has ever produced of the one conviction that has driven all of human curiosity since the beginning. The universe is large, we are here, and we want to know if anything else is too. The search goes on, quietly, steadily, one photon at a time, into the long and beautiful and terrible and endlessly surprising dark.